but we might now pass the baton to John Lynch, who's similarly going to present to us on his undergraduate thesis. John, also a graduate from AMC, joined BMT in January, now working in C5000. So John, without stealing your thunder, over to you. Thanks.
Yeah, thanks, Warren. I'll just share my screen. All right, everyone got that?
Yes, yep, that's good.
All right, yeah, so I'm a naval architect, but my thesis last year had more of a ocean engineering flavour, where I chose to investigate how an artificial reef submergence affects its ability to attenuate incident wave energy. So the research conducted aims to provide a potential solution to coastal erosion in Bustleton in WA, though it may also be applied to any coastline anywhere with a wave environment. Now, coastal erosion is the is the removal of shoreline sediment due to rising sea levels and wave action, and this can result in land loss, which is damaging to both coastal environment and the coastal environment and any infrastructure situated along that coastline. An example of such damage is shown in the figure there, though it can be to a greater extent than this, where it's just a wooden okay, so I'm just going to have a drink of water and go on mute real quick. So one solution to preventing the extent of such damage is to attenuate any incident wave energy before it reaches the shoreline. And here we have some structures that have been deployed to attenuate that energy. So the top left, we have a groin extending from shoreline, and on the top right, we have a breakwater. So breakwaters are very effective in attenuating wave energy, though they're costly to install, disruptive to the marine ecosystem, and they're also an eyesore on the coastline. Groins work well in preventing longshore sediment transport, though the accretion on the upcurrent side and erosion on the downcurrent side changes the beach topography. So you have the Great Barrier Reef on the bottom left there, which is a naturally occurring wave attenuation structure. So 84% of incident wave energy is dissipated across the reef flat. You can see that's where the waves are breaking. And then 64% of the remaining energy is 84% is dissipated across the reef crest where the waves break, 64% of the remaining energy across the reef flat. So emulating this with an artificial reef has added ecological and social benefits to that of attenuating incident wave energy, as the structure provides a habitat for marine life, which in turn provides opportunity for recreational activities such as fishing and diving. So on the bottom right there, you can see Bombora reef modules, which are a product from Subcon Blue Solutions over in WA. And here they're deployed to form an artificial reef in Monchoisie, Mauritius, to combat coastal erosion over there. So they've been proven to stabilize shorelines, though their success in doing so is really dependent on the coastal environment in which they're deployed. And this is the incident wave events they're likely to experience and varying levels of reef submergence due to tidal fluctuations of the area. So the aim of the testing was to quantify the artificial reef's attenuation performance across the tide cycle at Bustleton. And this is done by investigating its wave attenuation performance at 3 different submergence levels, representing the mean or the low, mean and high tide conditions at Bustleton. So scaled versions of the Bombora artificial reef module are used to configure the reef in the Australian Maritime College model test basin. You can see those scaled modules there in the figure or in the image. So the whole pattern in the modules provides habitat for marine life and forms a porous reef structure. This porosity adds to their ability to attenuate wave energy. And 6 regular wave events were investigated at each condition. Their height and period corresponding with the significant wave height and peak period of wave environments experienced at Bustleton. The wave attenuation performance is quantified by calculating the transmission coefficient, which is the ratio of wave height measured behind the reef to that measured in front of the reef. So the smaller the transmission coefficient, the more wave energy is attenuated. So here we can see the experimental setup in the model test basin. The reef's located centrally in the basin to avoid any influence from the sidewalls, and wave heights are measured using twin wire wave probes that capture the free surface elevation. The incident phase probe positioned in front of the reef and just off to the basin wall to avoid reflections from the front of the reef face. And 7 transmission probes are positioned within the reef's protected area to capture a spread of the transmitted wave heights. So the boundary of this protected area is the half ellipse you can see, and it's a function of the reef length, which is the length of the module rows. So due to the symmetry of the setup, transmission probes are placed along the reef centerline and to one side to increase the precision of transmitted wave measurement. So MATLAB software is used to process the free surface elevation data, firstly by cropping all probe data to include only the steady state, which is shown by the red box in the figure there. So the elevation data experiences a ramp up region as the wave makers build towards a target wave height. And this is evident through the increasing amplitude of the first few wave oscillations. And then there's also a region where reflections from the back of the basin influence the measured data. So cropping to the steady state eliminates the effect of these on the analyzed wave height data. So the data is then phase averaged to produce a single wave oscillation representing that measured at the incident wave probe and at each transmission wave probe. During the phase averaging process, each oscillation in steady state is considered a repeat observation of the averaged wave amplitude. So the phased averaged wave amplitude is then used to calculate the transmission coefficient value. So with 7 probes, there's 7 transmission coefficients for each wave event. So here are the significant transmission coefficients for each wave event at each submergence level. Significant transmission is just the mean of the highest third of the transmission coefficient values recorded for the 7 probes, in the same way that it is used to quantify the wave height or the height of a seaway. Here it is shown against wave steepness, which is a representation of the wave's free surface profile, and which is just a function of both the wavelength and the amplitude. So you can see in the figure shown that waves increasing from a steepness value of 0.012, the attenuation performance of the reef increases across all 3 submergence levels, though the overall attenuation performance is much better for the shallower submergence. For waves less steep than 0.012, the incident wave amplitude and the wave length must be considered. So on the top, we have the wave attenuation performance shown to increase as the incident relative wave amplitude increases, and the relative amplitude is just the wave height in relation to the reef module height. So this becomes the determining factor in transmissivity for waves less steep than 0.012 at the mean and deep submergence level. And on the bottom, you can see the reef's attenuation performance is shown to decrease as incident wavelength increases. Now, relative wavelength is just the incident wavelength in relation to the reef's length. So this becomes the determining factor in transmissivity for waves less steep than 0.012 at the shallow submergence level. And whether amplitude or wavelength is the determining factor of the less steep wave events transmission, it has to do with how the wave behaves when it actually encounters the reef. So here we have the longest incident wave event investigated at the shallow submergence level. And you can see the wave crest breaking upon encountering encountering each reef row, and that the modules are actually piercing the free surface in the troughs. So for waves less steep than 0.012, the wavelength determines transmissivity when breaking is observed. So this is the same wave event at the mean submergence condition. So you can see the wave crest begins to break upon encountering the first row, though not to the same extent as seen at the shallow condition. And the reef modules stay fully submerged throughout this wave event. So at this condition, wave amplitude becomes the determining factor for transmissivity for the waves less steep than 0.012. And so here we have the deep condition where the waves did not break and there's no cresting observed throughout the event. And this wave possesses great transmissivity, and only the steepest waves investigated at this condition showed any energy, or showed some energy attenuation. So here we have the mean significant transmission coefficient, which is just the mean of the significant transmission coefficients in the previously shown plot. And it's just a way of representing the overall attenuation performance for all wave events that are tested. So you can see the wave attenuation performance for the reef decreases significantly from, decreases significantly from shallow to mean submergence, and then only by a small amount from mean to deep. This shows how much the braking behavior of the waves affects the overall attenuation performance of the reef. So where braking is observed, there's an added turbulence component, which leads to energy dissipation. And where wave braking is not observed, there's only energy dissipation through the turbulence of the wave particles traveling through the reef structure. So as submergence levels get deeper, less of the wave particles interacting with the reef, leading to less energy dissipation. So here we have some surface plots showing transmission coefficients in the protected area behind the reef. So X is the distance from the back edge of the reef, and the y-axis is the reef's centerline, and wave direction is in the positive X direction. So moving from right to left in all plots. So the calculated coefficients are shown at the probe locations, and the 3 probes are reflected across the reef centerline as per the symmetry assumption. And these plots show the effect that diffraction has on the transmitted waves behind the reef. The probes and areas showing high transmission coefficient values indicate constructive interference occurring, where 2 waves diffract from the reef's back edge to meet, and their crests are superimposed from a wave to form a wave that is considerably larger to those surrounding it. As submergence increases, this area of constructive interference moves closer to the back edge of the reef, until at the deep submergence level, very little wave energy is attenuated and the wave goes straight through. The probes behind the reef at the shallow mean submergence level show good transmission values. So you can see the adverse effect that diffraction has on wave attenuation performance of a reef. So the influence of diffraction is also dependent on wavelength, which is shown here for 3 different wavelengths at the mean submergence level. As the incident wavelength decreases, the location of constructive interference moves closer to the back of the reef. And on the left figure, you can see that the transmission coefficient recorded at the probe furthest back in the protected area is 1.09. This represents a transmitted wave height that is higher than the incident one, which presents an issue that if the wave diffraction is not considered in implementing an artificial reef, you can actually increase the incident wave energy at some locations on the shoreline. This constructive interference is only present in experimental testing due to the constraint on reef length, and should not present an issue in deployment if the reef is sufficiently long such that waves diffracted from its edges do not meet before being incident on the shoreline. So what does this mean? Well, the reef can be expected to perform well for the low water half of the tidal cycle, offering approximately 12 hours of protection per day, as the Buston area experiences a diurnal tidal cycle with 2 periods of low and high water every 24 hours. Attenuation performance of the reef increases with incident wave steepness. This is beneficial in preventing significant erosion, which may occur during storm events, often characterized by steep waves. And to increase the attenuation performance of the reef, it could be deployed such that its relative submergence is reduced across the cycle, the tidal cycle. So wave breaking would be initiated more often, and at high tide, more of the wave particles would be interacting with that reef. The reef may experience some drying at low tide if this is the case to decrease its relative submergence in deployment. This may be considered detrimental to the coastline aesthetic, though still not as bad as implementing, or still not as obtrusive, sorry, as implementing other wave attenuation structures. And it would still provide a suitable habitat for marine life, retaining both its ecological and social benefit. So a few things that I considered for any future research in this area is to test in a more realistic seaways. So looking at how the reef performs for irregular incident wave events that are representative of that Busselton environment, and testing the reef for a drying condition where the modules pierce the still water surface. Also investigating the relationship between relative submergence and wave attenuation by producing more data points. And this could be done through developing a numerical model and validating it against the experimental data. Module design could also be explored, where the porosity of the module with the porosity of the module and how that affects wave attenuation. Another thing that could be explored is the reef profile by positioning reef rows at different heights, imitating the profile of a natural reef, which is shown in the bottom figure. Can also explore different reef configurations, such as the sawtooth shape shown in the top figure, or you could use a shape that may facilitate recreational activities, such as manipulating the wave breaking behavior to produce a surfable wave or something like that. And that is all, folks. Thank you very much.